All right, so think about this for a second. Right now, on millions of computers all over the world, there's this hidden war going on. It's this constant battle of wits between malware authors, the folks trying to steal and disrupt, and the security analysts who hunt them down. So let's pull back the curtain on this invisible battlefield.
And that really is the million-dollar question, isn't it? I mean, malware is built from the ground up to be sneaky, to operate in the shadows of your system. So how in the world do you track something that's entire purpose is not to be found?
Well, the answer is you've got to become a detective, a hunter. See, malware analysis isn't just about staring at code. It's a full-on strategic pursuit. You have to learn to anticipate its next move, get inside its head to understand its motives, and then you lay the perfect trap.
Okay, so before we can catch our adversary, we need to know what we're up against. We need to understand what it's trying to do. What are its goals once it actually gets inside a computer?
And this is where things get interesting, because you've got two totally different philosophies of attack. On one side, you have botnets. Think of these as vast zombie armies of infected machines all controlled at once to launch these massive widespread attacks. It's the sledgehammer approach. But on the other side, you have rats, or remote administration tools. These are the scalpel. They're for targeted one-on-one intrusions, giving an attacker deep surgical control over a single, really important machine.
And here's one of their sneakiest hiding tricks. Instead of running as some obvious, suspicious new program, malware loves to use a technique like DLL injection. What it does is it basically hijacks a program you already trust, like your web browser, and forces it to load and run the malicious code. Think of it like a spy who doesn't sneak in themselves. They just trick a trusted palace guard into carrying their secret malicious package for them.
Okay, so the malware is clever. It's hiding in plain sight, covering its tracks. So how do we fight back? We need a way to see what's really happening under the hood. And that brings us to the analyst's most powerful weapon.
Right? If this thing is operating in the shadows, how do we shine a light on it? We need, I don't know, some kind of special microscope? Something that lets us peer inside a program while it's actually running?
And that's where these two heavy hitters come in. On one hand, you have a disassembler. You can think of that like a static blueprint of a building. It's super useful for seeing the structure, but it doesn't show you what's happening inside. A debugger, on the other hand, that's like having live security camera feeds in every single room. It's a live, interactive view that lets you follow the program's every move in real time. For this kind of work, the debugger is absolutely king.
And just so you know, this isn't some abstract theory. These are the real-deal tools of the trade. Names like OllyDBG, X64DBG. These are the bread and butter for security analysts out in the field doing this deep, live inspection every single day.
So what's it actually like to use one of these things? What does a debugger let you do? Well, it basically gives you a superpower, the ability to freeze time inside a running program and just look around.
So the basic workflow kind of goes like this. First, you either launch the malware inside the debugger's protective bubble, or you attach the debugger to a process that's already running and looks suspicious. Then, and this is the magic part, you pause it. You set what's called a breakpoint to freeze the program in a critical moment. And once it's frozen, you can inspect everything. You can see what's in its memory, what numbers it's crunching, all to figure out exactly what it's up to.
And right here, this is where the real cat and mouse game kicks off. Because the second an analyst attaches that debugger, the malware might know it's being watched. And that starts this incredible, intricate dance of moves and countermoves.
So the analyst's first move is usually a software breakpoint. It's pretty straightforward, but really clever. The debugger literally goes into the malware's own code and swaps out the first piece of an instruction with a special code, this little byte, 0xCC. And that byte basically screams, "Stop!" to the computer's processor and hands control right over to the debugger. It's a digital tripwire.
But you knew there was a but, right? The malware authors are smart. They know this is the go-to trick. So sophisticated malware will actually scan its own code. It does a little self-check, and if it finds that 0xCC tripwire where it shouldn't be, it knows. It knows the debugger is there, and it can just shut down or completely change its behavior.
Okay, so the analyst needs to go into stealth mode. And that's where hardware breakpoints come in. This is the ghost trap. Instead of changing the malware's code, this technique uses special little memory slots built right into the CPU itself to set the trap. The code is never touched. This makes the trap completely invisible to the malware's self-checking routine.
You'd think that would be checkmate, right? Nope. The game goes on.
The most advanced malware, we're talking stuff that gets the highest level of system privileges, can sometimes find those same special CPU registers and just turn off the analyst's trap. The cat just figured out how to disable the trap.
So it's not just about setting traps. A really good analyst learns to read the malware's body language. Sometimes the way a program acts when it's under pressure tells you everything you need to know.
So think of it this way. When any program hits an error, it kind of throws up its hands and says, "Help." That's called an exception. Now, when a debugger is watching, it gets the first chance to see that error. If it does nothing, the program itself gets a chance to fix it. But if the program also fails to fix the error, it's thrown back to the debugger. That is a second chance exception.
And that second chance exception, that is a huge flashing neon sign for the analyst. It means the program hit an error so bad that it would have crashed and burned if the debugger wasn't there to catch it. This is basically the malware throwing a tantrum. It's a sign that it has detected the analyst's environment and is trying to self-destruct rather than give up its secrets. And that tantrum is incredibly revealing.
Okay, so we've seen the malware spot our traps, we've seen it freak out when it knows it's being watched, but the most mind-bending trick of all is when it uses the analyst's own tools against them.
Okay, stick with me here, because this is brilliant. There's this thing in the CPU called a trap flag. It's a feature designed specifically for debuggers to let them step through code one instruction at a time. So what does the malware do? It turns this flag on by itself. Then it runs a single instruction and waits for the exception that the trap flag is supposed to cause. But if a debugger is attached, the debugger will catch that exception first. So if the malware's own exception handler never gets the signal, it knows. It knows a debugger intercepted it. It's using the hunter's own tool to detect the hunter. It's just amazing.
So wow, after seeing this incredible back and forth, this chess match of traps and counter traps, and this wild psychological warfare, what's the big takeaway from all of this?
The big takeaway is that this game, it never, ever ends. This isn't just about hiding anymore. It's a full-blown intellectual arms race. The most dangerous malware and the most effective analysts aren't just masters of their own tools. They're masters of their opponents. They're constantly adapting, constantly turning each other's strengths into weaknesses. And that is a battle that will keep going as long as we keep writing code.